What's up, everybody? This is Cation. This is where we left off-ish at the end of lecture, and we talked about some simple hydrohalogenation reactions, the traditional ones where we're doing Markovnikov style, and we have the option of getting a more highly substituted carbocation in these examples. So we see these tertiary, secondary, and then again tertiary examples of carbocations. We went on and just briefly talked about this anti-Markovnikov situation, and that leaves us here at this carbocation rearrangement section. And this is the part where, to keep us on track, since we'll be talking about carbocation rearrangements in other contexts in this class, I'm making this executive decision to present this page only. This is page 3 of lecture 11, just this page in video format, so that we can stay on track with our class. So what we have going on here is this idea that we could have hydride and alkyl shifts in these halogenation reactions, hydrohalogenation. And the objective is going to be really simple, is like, what if it's possible to get an even more highly substituted carbon? And so this comes up in examples like you see below, where we have a primary carbon, a secondary carbon, and ooh, check it out, a tertiary carbon nearby. And here we have the products that are given, so you can get an idea that, it's not just the one expected product. This is a somewhat unexpected product, and maybe we're surprised and we go, what? But here, and I'm going to cross this out because I don't want you to worry about whether it's 50%, 50%, or 49, or like 75 or 50. It's just the fact that we could have this one is another product, right? And we would be responsible, you would be responsible for predicting that. So I want to give you a really good clear explanation for how you would come up with that. And what we're going to do is we're going to first just go with what we know. We're going to do this nucleophilic attack on the hydrogen, or this proton transfer, picking up that proton, and we're going to kick those electrons onto chlorine. That's going to give us an intermediate like this, where we still have the same main carbon chain, and we have the new hydrogen added to that primary carbon. So there is a new hydrogen there. There's now 3 where there once was 2, and now we have a carbocation left over on that secondary carbon. So again, that arrow means that the 2 electrons that were once shared between the 2 carbons in the pi bond, right, the pi bond becomes a new carbon hydrogen bond, and then we lost our chloride. Okay, so if we hadn't told you any differently, you may have expected that chloride to just go right ahead and attack that secondary carbocation, and that would be this product. And that would be the end of it. But since we're learning more about carbocation rearrangements, since we see that we have, once again, this is a secondary carbocation, but there's a tertiary carbocation nearby, well, now we're considering carbocation rearrangements. So I'm just going to copy this. Remember, we don't draw 2 different mechanisms on the same structure. So I'm just redrawing that same carbocation again, so we can highlight what's happening in the unexpected product. Now, some of you may be comfortable with predicting how hydride shifts occur, so just knowing what to do from here, but some of you maybe don't. So I'm going to do this in reverse. And by that I mean, I'm going to look at this given product, and I'm going to say to myself, what must have been the last step of that reaction? And so what I mean by this is that this must have come from a tertiary carbocation, because here this is a tertiary chloride. So it must have come from that tertiary carbocation. So now we've just greatly simplified our problem if we've identified the last step of this reaction is the chlorine negative attacking the partial, or attacking the carbon with the positive charge. And so that's the last step. The only thing that we're missing is this little middle step. So how do we have this carbocation rearrangement? How does that actually occur? And I think a great way to figure that out is to do some bookkeeping, is to do some decoding. And so we look at the 2 areas that are different. This tertiary carbon here has 1 hydrogen, whereas you can see in this next part, the tertiary carbon right there, that has no hydrogens. Over here, the secondary carbon had 1 hydrogen. And over here, the secondary carbon now has 2 hydrogens. So we actually moved this tertiary hydrogen along with its electrons over to that carbocation. And this is how we show that. We start our arrow, really zoom in. You can really see, we start our arrow at the carbon-hydrogen bond and we end at that secondary carbocation. That means that we're breaking the bond between the tertiary carbon to hydrogen, and we're forming a bond between the secondary carbon to that hydrogen. And that's how you do a carbocation rearrangement product when the products are already given. Okay, so I recommend pausing and going over that, talking through it again or listening again. We're going to take a look over here. There's a little bit more left blank. I just didn't give spaces for it. I'm going to go through the same type of explanation, meaning I'm going to start out with the UJ. I'm going to start out with the pi bond attacking the hydrogen, kicking those electrons over. That would give us an intermediate like this. Okay, this is our secondary carbocation. And if we weren't expecting a carbocation rearrangement, or if you didn't notice it or whatever, you would just expect that bromine to come in and attack that secondary carbon, and there's your product. Okay. Turns out that the major product is actually a little bit different. And in order to do that, we're going to think about how, maybe even why, we get something different. So that is not the secondary carbocation that leads to that product in one step. There's more involved. I'm going to do the same thing we did up above. I'm going to work our way backwards, right? So this one is a tertiary bromide. It must have come from the attack of bromide on that carbocation. So all of this one here is this molecule without the bromine, but instead it is a vacant p orbital, or just vacant space for which the bromide could then attack. Meh, meh. All right, so once again, we've simplified our problem. Now we just have to figure out how to do that, right? And this is already titled as an alkyl shift. The difference here between the alkyl shifts is that there's quaternary carbons involved. That's when you see an alkyl shift, as opposed to hydride shift occurs when you have tertiary carbocations that are next to a primary or a secondary. Okay, so really if you see a quaternary carbon, meaning you have this carbon right here is attached to 4 other carbons, we call that quaternary. That may be like a flashing sign for alkyl shift. So when we take a look at our structure, that red structure to the right, we see we have an extra methyl group down here that came from here. We have the same number of carbons. This is a rearrangement reaction, again, where we're not adding or removing any atoms from the molecule as the net result. What we're doing is we're shifting or moving one of those methyl groups. And the way we do that, again, is with one arrow. We start at the carbon-carbon bond, and we end at the carbocation. So what that means is that arrow specifically means that we're forming, let me say breaking first. We are breaking the bond between the quaternary carbon and that methyl group, and we're forming the bond between the secondary carbon and that methyl group, or specifically and that carbon. So that's what's happening in that carbocation rearrangement, all the while to get us from a secondary carbocation into a tertiary. And that's what happens. Right? You're going to see a lot of these come up in your homework if you haven't already, and that is my recommended method for doing that. If you weren't actually given the products, say we're like starting here and you didn't really know where you're going, you weren't given anything like this, and once again you just check it out, you see that you have that quaternary carbon right next door to a secondary, or it could be a tertiary carbon, but if it's right next door, then you're going to expect one of those methyl groups to move from the quaternary carbon and over to the one next door. Okay, what I have here below, actually, I guess there's no harm in just like showing the key, because I'm going to post the key anyway. But this here is a reaction puzzle that you're going to see at the end of most, if not all, of future lecture notes, where I do my best to give you like a big picture idea and combine as many different reactions as I can into one puzzle. So you see the key here, maybe just like forget what you saw, and then go through and work on it on your own, bring them up in discussion, and you can even make your own. So that'll be good times. Thank you very much for listening and watching, and I'll see you soon.